Awesome. Okay, so this one. Unless you want to move around a lot, you can use that one.
Let me see there.
All right. I want to commend all the speakers. We're only 15 minutes behind at this point after a long day. This is pretty awesome. You guys rock. I'm very happy that we have Thialita here to give the next talk. I'll remark that we have some extra posters and poster tubes. If you want to put a poster, I'll stick it in the commons room. I'll be quiet.
All right. Hello, guys. First, I'd like to thank the invitation to participate in the conference and also the responsibility to close the day with the last one. I know you look at regularity estimates for fully nonlinear equations and you may think, well, that doesn't sound like geometry. Right? So my main goal is to convince you that this should be interesting for you too. Let's hope I'm successful. So we start with the outline of the presentation. My goal is to publicize regularity theory, so I do not hope to be too technical. So I'm going to start with some heuristics considerations of the theory, then give you a quick tour on the fully nonlinear theory, and then present and give sharper regularity estimates of the past few years. Right? So we start with what is a diffusion process, which is a tendency of some physical phenomena and sometimes social phenomena to give a random movement or a spreading movement some sort of equilibrium. So my phenomena will tend to pursue an equilibrium position. So we can see this in thermodynamics, elasticity, probability, other branches of science and other branches of mathematics like geometry. And what is ellipticity? Well, ellipticity or an elliptic operator describes some sort of balance between, well, or how much the graph of a solution will bend towards each direction. So my picture here is a well-known surface, right? It's what we teach our Calc 3 students, but it's a harmonic function. And on our left-hand side, I have a minimal problem or minimizer problem, solutions to a convex or minimizers of a convex energy functional, or you usually satisfy an elliptic equation, usually a Euler-Lagrange equation. For example, one of them is the Laplace equation for harmonic functions, or the minimal surface equation will also satisfy a convex energy minimal problem like this. And of course, you have the Hessian equations, which are more explicit equations involving the eigenvalues of the Hessian of your solution. Okay. All right, so we describe what diffusion processes or what elliptic operators are, and we see that we have a connection between. So diffusion processes are better described mathematically using elliptic operators. And what about regularity? Where does regularity comes into the play? So if we start with the Laplacian equation, we know that solutions to the Laplace equation have a special property, which is the property that the value at a point x equals its own average in every scale. So this is known as the mean value property. And here we start to see levels of regularity that are required to satisfy my Laplace equation. On the left-hand side, we have the Laplace operator, and solutions to that requires at least that my function is twice differentiable. On the other hand, with the mean value property, my solutions or my function to satisfy the right-hand side only needs to be at least L1 log, or at least locally integrable. Okay? So if you have, we know now that if you have a continuous function h, which is also in L1 log and satisfies the mean value property, you can go back to the Laplace operator. So functions that satisfies the mean value property and are also continuous or actually C2. They are C2 and they will satisfy the Laplace equation. Sorry, can I say that again? Is XU? Oh, HU. Yeah, that was a typo. Sorry. H is should be U. Yes. Yes. Thank you for spotting that. Okay, so that where regularity techniques come into play. You start with an H1 log function, with L1 log function, which are also continuous, and you'll using techniques of regularity, you end up with a H1 with a C2 function that will also be harmonic, right? So you end up with a strong classical solution. So that's what regularity does. You start with a weak notion of solution, then you add some regularity techniques, and you end up with a strong classical solution. So if you want to prove existence and uniqueness of strong solutions, you can use regularity techniques. All right, so now for fully nonlinear equations, let me start with the following problem. You have a fully nonlinear equation given by f cation of u at a point x equal a continuous right-hand side, where my f is a uniformly elliptic operator, and that means the operator will satisfy some sort of Lipschitz condition on the matrix argument for some positive constants lambda and capital lambda. In particular, if you have an equation with measurable bounded coefficients in which those coefficients are given in terms of a matrix, you can say that this is equivalent of saying that the eigenvalues of the coefficient matrix are all in between lambda and capital lambda. Okay. As for examples of fully nonlinear elliptic operators, well, the simplest one I can start with are the Puch extremal operators, which are basically weighted sum of the eigenvalues of the matrix. So the minimal Puch operator, which is the first one, puts a heavier weight on the negative eigenvalues, while the maximal Puch operator gives a higher or heavier weight on the positive eigenvalues. And in fact, every fully nonlinear elliptic operator is related to the Puch operators. And I could have started with, I could have defined elliptic operators, uniformly elliptic operators, by this relation with the Pucci operators. Another example I can give comes from the Isaac equations, which appear in differential games theory and other Brownian motion equations. And the second one, I'm sure we have heard a lot of this one before, is the special Lagrangian equation. And this is special, not only because it's the special Lagrangian, but because we see that regularity properties of the solutions gives you geometric properties of the manifolds described by the solution. All right, and if you want to develop a regularity theory, you need to start with a notion of weak solution. For the fully nonlinear setting, the best idea of weak solution comes from viscosity solution. And we say that a continuous function is a viscosity sub or super solution if, looking at the graph of U, if you can touch U by a paraboloid or a smooth function at a point, at that point, the touching paraboloid will satisfy the equation or the inequality in a classical way. So we pass the responsibility of satisfying in a strong sense the equation to the smooth tangent paraboloid. All right, now comes a crash course in regularity theory. The first regularity results we had for the fully nonlinear setting comes by Krylov, Samsonov in late 70s and early 80s, when they proved a Horner type inequality for linear elliptic equations in non-divergence form. At that time, we only had Horner inequality for divergence form equations, and then these were a major breakthrough in the theory when they developed a nonlinear argument, even though they were working with the linear elliptic equations, the argument they used were nonlinear, and that opened the door to the fully nonlinear setting. So with this, now solutions of the homogeneous equation or C1 alpha locally for some alpha between 0 and 1. We still don't know what this alpha looks like, but we do know it exists. And in addition to that, Evans and Krylov, under the additional assumption of convexity of the operator, solutions of the homogeneous equation or C2 alpha locally, again for some alpha between 0 and 1. So this tells me that the derivatives, the first derivatives are Hilde continuous, and in the case of the convexity, the second derivatives are Hilde continuous. Okay. So now let me give you some heuristic justification on how you can expect solutions to be C1 alpha or C2 alpha. Okay. All right, so we start by assuming you can differentiate the equation in some direction. And if you do this, your right-hand side remains 0, but your left-hand side, right, looking at this Fij as a now matrix of coefficients, you go back to a non-divergence form equation. And so you can apply Krylov-Samsonov theory and to conclude that your derivatives will be Hilde continuous, and so you can expect to be C1 alpha. Okay. Under the addition of convexity or concavity, say, if you take the second derivative of the equation at the same direction, you end up with this two-term sum. And then using concavity, let's say, you end up, since the sum gives you 0, you have that the first term should be non-negative. And so again, you have a non-divergence form type equation here. And so you can apply Krylov-Samsonov again to the second partial derivatives. Those second partial derivatives will be C0 alpha, and then U is expected to be C2 alpha. So this is far from being a rigorous proof. It's just to give you an idea on how to connect the dots here, or how to expect solutions to be C1 or C2 alpha. All right, and what about without the assumption of concavity or convexity on the operators? What can we say about the regularity of the Hessian or regularity of the second derivatives? So that's when we start W2 epsilon theory, which was first observed by Linz Evans and later Caffarelli-Cabré, where they started with a non-divergence form equation. And again, if A is a matrix of coefficients, where the eigenvalues of this matrix are all in between lambda and capital lambda, solutions to this homogeneous equation belong to the Sobolev space C to epsilon, W to epsilon. That means the Haitian is integrable with epsilon in the exponent. So it's in L epsilon. For some epsilon, again, unknown, but in which we do know it depends only on dimension and the ellipticity constants. So it's a universal constant. All right, and here it's good to note that we have no assumptions on the coefficients. You can assume that they are measurable and bounded, but no other continuity assumptions are made, which is good for us. And again, the Haitian integrability exponent is widely unknown. We do not know what those exponent regularities are, but we do know they exist. And detail, they might not be unique. All right, so how do I connect this with fully nonlinear equations? Again, using the Pucci operators, since I can relate every fully nonlinear uniformly elliptic equations operator with the Pucci operators, if I have and the Pucci operators are related with my previous equation, the non-divergence form, in which the matrix of coefficients have eigenvalues bounded by lambda and lambda. If I have this for a super solution of F, then I have the same result as with the non-divergence form equation. All right, so what is the advantage of knowing that my Haitian is in the L epsilon space? One of them, one of the applications came in 2012 by Armstrong, Sylvestre, and Smart, where they showed that even without the assumption of convexity or concavity of the operator, you can still expect the solution to be C to alpha up to a singular set, where the singular set has house of dimension at most dimension minus epsilon, where your epsilon here is the very same exponent of the W2 epsilon estimates. Okay. So in other words, the better W2 epsilon estimates you have, the better control you have on the size of the singular set where your solution failed to be smooth. Okay. So this is another breakthrough in the theory. And you may ask if before I didn't have regularity results without assumption of convexity or concavity, can I in the future get rid of the singular set? And the answer is no. The answer actually came before that by Najarashvili and Vladu in a series of papers where they constructed solutions whose Haitian blow up. They were actually unbounded. They did more than this. For every alpha between 0 and 1, they constructed a uniformly elliptic operator whose solutions fail to be even in C1 alpha. So that means singular sets are unavoidable for the general theory of fully nonlinear equations. So you cannot totally get rid of set where my solution failed to be smooth. So the best you can do is to control the size or the house of dimension of the singular set. So again, to better control the size of the singular set, you need to have better W2 epsilon estimates. And so the pursuit for better W epsilon 2 estimates began. And in that same paper, Armstrong, Sylvestre, and Smart, through an explicit example, they proved that 2 over the ellipticity ratio plus 1 is an upper bound for my integrability exponent. It's a universal upper bound. That means every super solution to a fully nonlinear equation is in W2 epsilon for some epsilon that cannot be greater than that upper bound. So that's the maximal minimal integrability for all solutions. And so, not surprisingly, they conjectured that this should be the optimal minimal integrability of the theory. And so this has become a major conjecture since then. And so many works followed this conjecture. To start with, we have the work of Nonlinear in 2018, where he managed to improve the decay in terms of the ellipticity ratio and the dimension, which before was an exponential decay. And now we know it's a polynomial decay with respect to the ellipticity ratio. And in 2019, Connor Mooney improved even further the degree of this polynomial decay, but then the dimensional constant is decaying, it's going to 0 more rapidly than it was before. So you gained something, but you lost something as well. And again, in following this, me with Eduardo Teixeira, which is currently my PhD advisor, we managed to give improvements on both estimates, the upper and lower bounds. We showed that for super solutions, the optimal integrability exponent of the theory belongs to this interval where my upper bound, my new upper bound, actually solves the conjecture in the negative way. So the conjecture doesn't give the best optimal operator, the best optimal exponent for every solution in any dimension. For higher dimensions, you can find even smaller values that will serve as an upper bound for your epsilon. And for the lower bound, what we did was to improve the dimensional constant, which gives you a hint, right? Because this new sequence of constant that depends on the dimension, only on the dimension, will blow up as the dimension goes to infinity. This actually suggests that the sharp polynomial decay of the epsilon in terms of the ellipticity ratio should be less than d minus 1. So you should expect to be able to decrease the degree of this polynomial. We suspect that the sharp polynomial decay should be d minus 1, d over 2, instead of d minus 1. But this is yet to come. Do I have time? Do I have time? Okay. All right. So let me give a very brief points in the proof of this theory. For the upper bound, we extended the Armstrong-Smart construction to higher dimensions. They did in the two-dimensional case, and we extended this to higher dimensions. So for every value of epsilon, which is slightly bigger than this one we present, we can construct a solution which is bounded in D1, but whose Hessian fails to be integrable with the exponent. So that means this gives you a new universal upper bound for the optimal integrability exponent. And then for the lower bound comes from the L epsilon estimates, which means if you want to show that the Hessian is integrable, is in L epsilon, you can do this by showing this decay measure of the sets where my Hessian is very big. Okay? So what you do is you slice the set where the Haitian is very big into stripes. I don't think I have space here. And so you can choose the radii of your slices. Right? You cut the set where your Haitian is bigger than a certain number into slices. And instead of choosing a fixed value for your radii, let's say 2 powers of 2, you can delegate the choice of this best radii to a later optimization process. So instead of slicing the set into, let's say, powers of 2, you slice into powers of something that's bigger than 1. And another optimization process deals with the total number of negative eigenvalues of the Haitian, which shows up in the final estimate for epsilon, which is surprising. And then our results state that you can take your greatest lower bound as the sup of this function, where gamma here is just a change of variable from 1 plus delta. And C is the constant that depends on the dimension, the ellipticity ratio, as well as the number of the eigenvalues already optimized. So using this information, using the fact that if you have a super solution, at least you can guarantee that at least one of your eigenvalues will be non-positive. And so you can estimate this function by C, and using the fact that we have at least one negative eigenvalue, and find the constant we state in the main theorem. And you can see explicitly that this constant will blow up with the dimension, which shows actually that the sharp polynomial decay should be less than d minus 1. So I believe I can stop here. Thank you all again. I hope this was somewhat interesting to you. And thank you.